100 trillion years from now, the last of a great civilization hides in the darkness. Throughout their glory days, their engineers worked entire star systems. They dismantled planets and asteroids to construct an immense interstellar empire. But now, in the twilight of their time, all of this is long gone. All around them, the universe is dying as the last of the stars are going out. Over countless millennia, the sky has continued to fade into an eternal night, the aging universe gripped by desolation and decay. And so, in the darkness, they wait for the end. Long before they had realized it was coming, they knew that the universe was on a path of inevitable decline. Methodically, they hunted for a final place to wait out eternity, and embarked on their last great feat of engineering. Around a lost and lonely black hole, they built a new home. With demolished worlds as raw materials, they constructed a shell to completely enclose the darkness, and within this thin shell, barely withstanding the gravitational grip of their savior, they eked out their meager lives. The dwindling light of dying stars rained down upon their final home, whilst their swirling black hole was harvested to power their existence. But more than that, the black hole at their heart gave them the greatest gift of all. For the black hole gave them time. No one remembered the name of the great scientist who had discovered the nature of time. But the astro engineers knew that time was not the same across the cosmos. And here, within the immense gravity of the black hole, time trickled more slowly. Whilst many years passed outside, mere moments flashed by within the immense sphere, and so the last of the civilization watched the future play out in front of them. But they knew they had only delayed, not averted, their ultimate demise. And the darkness would inevitably envelop them forever. Of course, this story is little more than speculation, but it is built on a scientific idea that changed our universe. It's been more than a century since Einstein's relativity shook up our understanding of time and space. But how does it really work? And what does it really mean? Both time and space seem so commonplace, so obvious, so everyday, but beneath their ubiquity, they hide a multitude of unanswered questions. Questions to which Einstein's theories only begin to answer. What is space made of? Does time exist? And will hunting for their ultimate nature lead to sudden clarity? Or will space and time just become more elusive? Einstein offered them lunch, and they accepted. So he moved a whole bunch of papers from the table, opened 4 cans of beans with a can opener, heated them, stuck a spoon in each, and that was our lunch. Albert Einstein was a busy man and often missed lunch, and that was back in 1915. In the century since, our lives have only become more chaotic. And that is why a meal kit service like HelloFresh, our sponsors today, are such a great choice. HelloFresh delivers fresh, high-quality produce straight from the farm to your door with more than 55 weekly meal options. Great for everyone, and especially if you want to stay fit and healthy. I'm a big fan of fitness and eating the right food, but in honesty, sometimes there just aren't enough hours in the day, and a microwavable meal seems like the only option. HelloFresh has saved me from this tasteless horror. The kits are foolproof, genuinely really hard to get wrong, and that is coming from an absolute cooking disaster. And last but definitely not least, a recent survey found their meals up to 72% cheaper than dining out or grocery shopping. Go to HelloFresh.com and use the code HISTORY16 for up to 16 free meals and 3 surprise gifts. This is a great company, and the cherry on top is that they're also carbon neutral. A big thanks to HelloFresh for supporting educational content on YouTube. As the lonely world lingered on, its beating heart warped the very fabric of the universe around it. The civilization had done everything they could to keep going, to put off the inevitable. But try as they might, they could only bend reality. They could not break it. Behind it all is surely an idea so simple, so beautiful, that when we grasp it, in a decade, a century, or a millennium, we will all say to each other, how could it have been otherwise? How could we have been so stupid? What is space? The question seems almost meaningless. As children, we learn to describe our surroundings as up, down, left, right, back, and front. We call it three-dimensional and are free to explore each dimension. But just what is it, this universal platform on which we play out our lives? It is a question that occupied the minds of the earliest philosophers. In the 4th century BC, Plato declared that space was the nurse of becoming, a medium in which everything existed but with no qualities of its own, and his student Aristotle agreed that an empty void was impossible. But it would be more than 2,000 years before our concept of space was born. By the coming of the 17th century, modern science was crystallizing. The processes of the universe were being codified into physical laws, and the understanding of these physical laws was evolving from myths and stories to the language of mathematics. Of course, Isaac Newton was at the forefront of this revolution, but before he enters our stage, we must first start with a boat. In 1632, Galileo published his seminal work, Dialogue Concerning the Two Chief World Systems. He was in his mid-60s by this point, and had already had multiple run-ins with the Roman Inquisition for his assertions that the Earth rotated around the Sun. So, he had decided to skirt controversy and spend the intervening years quietly cementing his myriad ideas on space and the cosmos into a book. And at one point within this book, he muses on a boat. More specifically, the life of a sailor locked below deck in a windowless cabin, with plates, knives, and a goldfish in a bowl on the table, and a collection of birds, flies, and butterflies. Just what does the sailor experience? Tied up in port, the cabin is a picture of serenity. All is calm as the goldfish swims happily in his bowl. On the table, plates and cutlery remain in their place, and the flying creatures happily flutter about. But finding itself in rough seas, the cabin heaves and falls with the ship. Plates and cutlery are wrenched off the table, water spills from the goldfish bowl. On calm seas with wind-filled sails, the ship would speed up. The sailor would feel this change and see things sliding off the table. But when the wind finally drops, the ship sails smoothly on the glassy sea. Inside the cabin, all would be calm, serenity returning. For the sailor, it would be as if the ship was still in port and was not moving at all. A dropped plate would fall straight to the floor, and the sailor would sit comfortably in their chair. And it was here Galileo realized something. Without a window to reveal the truth, there are no experiments the sailor could do to reveal whether the ship was moving or not. He concluded, therefore, that there must be no absolute concept of being at rest in space. Instead, everyone must experience any smooth, uniform motion in the same way. All uniform motion must feel like simply being still. Galileo declared that any uniform motion is simply relative to any other uniform motion. And with this, the first theory of relativity had been born. Galileo's sailor floats gently on their ship on seas near the Earth's equator, rotating at 1,600 kilometers an hour around the Earth, which in turn orbits the Sun at 67,000 kilometers an hour, which in turn orbits the Milky Way at 720,000 kilometers an hour, which in turn is traveling towards the Andromeda Galaxy at 403,000 kilometers an hour. And yet, he feels nothing on this vast journey millions of kilometers from his starting point. Unfortunately, upon publishing the book, Galileo once again fell foul of the Church and was found guilty of heresy for his heliocentric view of the cosmos. The work was banned and would not be removed from the Church's Index of Forbidden Books until 1835. But this was not the end. For within a few decades of Galileo's downfall, two of Europe's greatest minds were arguing about the nature of space. One of them, Isaac Newton, was born in England in 1642 within a year of Galileo's death. He, of course, needs little introduction and is known now as one of the greatest thinkers of his age, perhaps one of the greatest of all time. And whilst not forgotten, his opponent, Gottfried Leibniz, is somewhat less well known today. Born in 1646 in what is present-day Germany, he was a leading thinker of his time, writing on mathematics and philosophy. He pondered deep metaphysical questions, including one that still haunts physicists and philosophers to this day: why there is something rather than nothing. It was in the development of calculus that the two men's feud began. Whilst Leibniz published his work first, Newton claimed that he had stolen his ideas. As president of the Royal Society at the time, Newton set up a committee to investigate the dispute. Unsurprisingly, the committee found in favour of Newton. And so, this animosity carried over to their second disagreement. A simple question: what happens to a spinning bucket of water? Space, Newton declared, was a universal absolute, a rigid stage on which motion was played out, and both space and time would exist in a universe devoid of matter to experience any motion. To argue his point, Newton asked us to think about a bucket of water. If the bucket sits at rest, the surface of the water would be flat and level. But if we spin the bucket, the water spins too, and its surface becomes curved. And so Newton asked, just what is the water spinning with respect to? He claimed that the acceleration of the spin was relative to an absolute space, something separate to the object itself, and so spinning a bucket in an empty universe would also curve the surface of the water. But to Leibniz, space in an empty universe, devoid of any matter, simply made no sense. The properties of objects, Leibniz claimed, are essential in defining their meaning. Space only had meaning in the relative locations of objects, and similarly, time only had meaning when discussing their relative motions. Without matter, Leibniz said, space and time simply had no role, and hence, no existence. Sadly, Leibniz died in 1716, with the argument still in full swing, and it was Newton's ideas that stuck. Absolute space, in its own nature, without relation to anything external, remains always similar and immovable. Absolute true and mathematical time, of itself and from its own nature, flows equally without relation to anything external. This so-called absolute space and time would be the accepted science for nearly 2 centuries, but with the caveat of Galileo's rejection of absolute rest. Relativity was still part of the argument. But that only applied to space. Time was a totally different matter. With its implicit direction, time appeared completely distinct. For Newton and Galileo, everyone's clock across the universe ticked with absolute synchronicity, a universal beat that ran through every event in the cosmos. 1 second on Earth, the same as a second anywhere else. But is this true? Is time malleable, or an unswerving metronome that drags the cosmos forward? Does time itself have properties, or is it defined only by the events that run in its current? To answer these questions, we must begin not with physicists wondering about clocks, rulers, and motion, but with heat. In the distant future universe, around the aging black hole, our dying civilization sits and waits. For sitting and waiting is all they can do. With the passing of the stars, raw energy had become the most precious thing. To preserve what they had slowed their very existence. Every aspect was focused upon survival as their sleepy eyes watched the ever-darkening skies. And as total, universal heat death crept across the cosmos, they realized that time was their ultimate enemy. You may see a cup of tea fall off a table and break into pieces on the floor, but you will never see the cup gather itself back together and jump back on the table. What is time? Like space, the nature of time occupied the minds of many ancient thinkers. In ancient Greece, Aristotle stated that time was simply the steps between before and after, whilst Hindu philosophers saw time as cyclical, from creation to destruction, over 4 billion years. But its true origin remained elusive. Like space, time seems to be something obvious, something that is just present. But it is clearly a different beast. We cannot, for example, freely travel through time. Unlike space, time has a direction, a distinct past, and a coming future. Of course, scientists can be pragmatic and not worry about the nature of time. Coupled with a ruler, a clock completes the experimenter's toolbox. But it doesn't mean we can ignore the question. And so to understand time fully, we first have to think about horses and steam engines. The coming of the Industrial Revolution presented humanity with a problem. The original engines of civilization, draft animals like horses and cattle, were relatively simple things. Understanding how much to feed them and how much to work them was easy. A certain number of bales of hay could guarantee a day's work from a well-fed animal. But what of newfangled machines, such as a steam engine? How much work can you get out of a heap of coal? This was an important question from an economic standpoint. Do you even bother to replace a horse with an engine if it is going to cost more to feed it? And it was out of this conundrum that thermodynamics was born. Many minds were wrestling over the question of the ultimate efficiency of engines. Indeed, at the time of thermodynamics' inception, a typical engine only worked at 3% efficiency. In a physical steam engine, the heat of the fire is used to boil water, but some of the fire's heat just radiates into the air. Metal scrapes against metal, screeching loud and hot to the touch, both forms of energy loss. In any physical steam engine, this loss of heat as waste is inevitable. And indeed, within the mathematics of thermodynamics, perfect efficiency was found to be an illusion. The concentrated energy released from burning coal must be degraded as it flows through the engine, and some must be lost into the surroundings. Eventually, a new measure was introduced to account for this increase of decay and disorder: entropy. And it is probability that dictates how this happens. As the early 20th century physicist George Gamow put it, "The room in which you sit reading this book is filled uniformly by air, from wall to wall and from floor to ceiling. And it never even occurs to you that the air in the room can unexpectedly collect itself in a far corner, leaving you to suffocate in your chair. However, this horrifying event is not at all physically impossible, but only highly improbable." Gamow goes on to give the waiting time of such an event: trillions upon trillions of times longer than the entire age of the universe. Disorder is always, statistically, far more likely. And so, through these new laws of thermodynamics, physicists revealed an inexorable growth in entropy as the universe marches on, a future universe destined to be more disordered and decayed than today's. And this applied not only to steam engines, but whole planets, stars, galaxies, filaments, all marching from order to disorder. It was in 1862 that the grim logical endpoint of these ideas was proposed by Lord Kelvin, for whom the measurement unit was named. Although mechanical energy is indestructible, there is a universal tendency to its dissipation, which produces exhaustion of potential energy through the material universe. The result would inevitably be a state of universal rest and death if the universe were finite and left to obey existing laws. And so, was this time? A constantly dying universe heading for inevitable heat death, stars going out one by one in a steady march from potential energy to waste, leaving the trillion-year-old universe dark and spent. One of the great minds to occupy himself with entropy and the arrow of time was James Clerk Maxwell, the iconic Scottish 19th century scientist. His views on thermodynamics shaped our understanding of heat and gases, and he did all of this with the assistance of a demon. Maxwell understood the implications of entropy. He knew that if he mixed two gases, one hot and one cold, the result would be warm gas. And he knew that the gas would stay warm and mixed rather than separating into two halves. But he wondered, what if we introduced a tiny demon who can sense each and every atom in the gas? This demon can turn around atoms, directing slow atoms to one side and fast to the other. As the temperature of a gas is a reflection of the average speed of its atoms, the demon could effectively separate the warm gas into two unequal halves, one hot and one cold. The demon seems to have broken the laws of thermodynamics. It has taken the disordered state, the warm gas, and created a more ordered state, hot and cold gas. And whilst this is only a thought experiment, arguments over the meaning of Maxwell's demon have raged for over 150 years. Some have stated that the demon must be expending energy to sort the gas atoms, and so total entropy will continue to rise. However, some have proposed that it is not energy that is important, but the fact that the demon uses information, namely the speeds of the atoms, to do the sorting. Linking energy, entropy and information might seem a little strange, but over the last 3/4 of a century, this link has become stronger and stronger, and as any touch of a computer will tell you, processing information generates a lot of waste heat. But the situation is even more complex than that, for it is not simply the processing of information that leads to waste heat, but the forgetting. When we add 3 and 2, the answer is of course 5. But if I told you an answer was 5 and ask what two numbers are summed together, you cannot answer. In a similar way, inside a computer, logic gates combine electronic signals to do the addition. Whilst two numbers are fed in, they are forgotten as the single answer is spat out. The calculation is irreversible, the inputs lost to the universe. And in the action of forgetting, the logic gates heat up just a little. In this way, thermodynamics provides us with the ultimate limit for forgetting. Called the Landauer limit, it is the inevitable release of energy from erasing a single bit of information, and at room temperature, it is just over 1/100th of an electron volt. Proven experimentally in 2012, scientists believe that at present computer chips produce thousands of times more heat than this limit, but by 2035 they will most likely reach it. That tiny bit of waste heat inescapably increasing the entropy of the universe. Ultimately, across the cosmos, it is this irreversibility of calculations that drives entropy to increase. Forgetting information is therefore an essential ingredient for defining an arrow of time. Does this mean that for yesterday and tomorrow to have meaning, we must forget? Is the existence of the future implicitly tied to our inability to remember? And it is now we can return to our lonely civilization on the brink of universal heat death in the far distant future. When all useful energy is used up and entropy is at maximum, would time even have any meaning? And so, we have now reached a turning point. The foundations of modern time and space can only get us so far, and though they are useful, there is another revolution coming. A new order that will lead directly to the last days of our lonely black hole world. And as we continue in our journey, we are going to have to explore new time and new space. Within their black hole shell, many of the civilization resigned themselves to their fate and dozed their way to the end. But a few curious minds, with their dwindling energy, still wondered about the universe. Great books that had existed for almost an eternity told them how space could bend and curve. Central to these books was the story of light. They knew that light speed was immense and had used it to help measure their empire. They knew that light was a limit they could never break, no matter how hard they tried. And they knew that the speed of light had been the first step in the long journey to understanding how the universe really worked. When you are next out of doors on a summer night, turn your head towards the zenith. Almost vertically above you will be shining the brightest star of the northern skies, Vega of the Lyre, 26 years away at the speed of light, near enough to the point of no return for us short-lived creatures, for no man will ever turn homewards beyond Vega to greet again those he knew and loved on Earth. The speed of light has always been mysterious. Early experiments in flashing lights back and forth had shown that it must be much faster than sound. So scientists wondered, was it infinite in speed? It was in 1676 that Danish astronomer Ole Rømer finally found the answer. Rømer was observing the moons of Jupiter as they circled the giant planet, and timing just when they entered the gas giant's planetary shadow. He had assumed that the orbits ticked like clockwork, and so would be able to predict just when the eclipses of the moons would begin and end. But as he observed the moon Io throughout the year, his predictions got steadily worse, and then better again. It became clear that the accuracy of his predictions depended upon our distance to Jupiter, and he would need to include the extra time taken by light having to travel further. And so, with Rømer's data, fellow astronomer Christian Huygens calculated that light must move at more than 211,000 kilometers every second, not far off our modern estimate of about 300,000. Rømer's observation confirmed that light was fast and finite, but precisely what light was would have to wait for 2 centuries. For as well as the confusing implications of James Clerk Maxwell's demon, he is also famous for intertwining electricity and magnetism into a single idea: electromagnetism. Light, he found, was nothing more than a self-propagating combination of the two, and written into these equations was light's blistering speed. But there was still a problem. Just what was this speed relative to? Maxwell's equations gave no answers, so physicists began to search for a solution. Perhaps, they hypothesized, light traveled in an invisible medium, a mysterious ether permeating the entire cosmos. But that would also imply an ultimate state of rest in the universe, a worrying thought, as this would break Galileo's relativity. The problem was severe. So whilst one group of physicists set out to measure the properties of this supposed ether, others took the evidence in front of them and made an even larger leap. And chief among these was a young Albert Einstein. Einstein wondered why electricity and magnetism would not obey Galileo's relativity. Why should experiments specifically using the flow of electricity or spin of a magnet reveal absolute motion? In a bold step, he declared that they cannot. And with that, the special theory of relativity was born. On Galileo's ship, Einstein proposed all experiments would yield the same results, whether the ship was secured in port or smoothly sailing on a glassy sea. Throwing a ball would of course not reveal whether the ship was moving, but neither would measuring the speed of light. The speed of light in a vacuum was constant. This final statement seemed to fly in the face of the universe as laid out by Newton. In Newtonian mechanics, you could simply add speeds together, and each observer would measure differing speeds dependent on their own motion. But according to Einstein, this was not the case for light. Everyone would measure the same speed, whether the ship was stationary, going at 50 knots, or 50,000. However, if this was true, something else had to give, and the only freedom in the equations was the very nature of space and time themselves. For it to work, each observer must have their own measurement of space, and each observer must have their own measurement of time. With special relativity, it was the speed of light that was absolute, not space and time. Space and time were no longer the universal stage on which physics played out. And just as Maxwell had combined electricity and magnetism, space-time, too, was about to unite. Gentlemen, the views of space and time which I wish to lay before you, they are radical. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. In 1908, Hermann Minkowski, Einstein's former professor, came up with an idea. In reaction to the revelations of special relativity in 1905, he had decided to explore the geometry of these new equations. In Einstein's formulation, space was space and time was time, and to transform from one observer's viewpoint to another, you needed to mix the two together. But Minkowski pointed out that it was simpler to mix space and time together into space-time, and to transform one observer's space-time to another through geometry. And so, finally, combined space-time was born. This new melding of the three dimensions of space and one dimension of time has come to be known as Minkowski space, though Minkowski himself tragically died in 1909, before his idea had been fully embraced by the physics community. Newtonian space and time may have been completely upended, but Einstein was still not happy. Though his ideas had revolutionized our ideas of the universe, they could not account for gravity. Newton's gravitational equations needed the distance between masses, and special relativity now told us that no one could even agree on what these distances were. So Einstein went back to the drawing board and spent a decade thinking about gravity. What eventually emerged from these ruminations in 1915 was a solution that shocked physics to its core. Einstein had taken Minkowski's geometric picture of spacetime and made both space and time bendy and stretchy, the presence of mass and energy producing this curvature. Within this general theory, Einstein concluded that gravity, as a force, simply did not exist. The effects of gravity were encoded within the curvature of space and time. Newton's picture of space and time was well and truly dead, for not only were space and time relative, they were flexible as well. The consequences of Einstein's vision of relativity were quickly uncovered. In the special theory, the relative ticks of clocks depended on motion, and whilst everyone feels time passing at 1 second per second, different clocks will tick off different amounts of time. But with the coming of the general theory, time was shaken even more, as where you are also influences the tick of your clock. The presence of mass curves space and curves time, and so gravity can dictate the relative ticking of a clock. The following year, in 1916, Carl Schwarzschild solved the field equations of relativity for a spherical mass, and written inside his equations was a completely collapsed mass, squeezed into a point. Whilst it didn't get its name for another 50 years, Schwarzschild had the mathematics for a black hole. His solution showed that black holes bend both space and time, and with this intense curvature comes intense gravitational pulls, not even light able to escape. In the vicinity of a black hole, where gravitational fields are immense, time becomes more and more curved as you get closer to the center. Compared to clocks in the distant universe, near the heart of darkness, time ticks very slowly. And it wasn't just black holes that sprung from the new equations. In the centuries since Einstein's gravitational insights, many more bizarre solutions have been found. Throughout the relativistic literature, there are wormholes, warp drives, and even entire curved universes, all built from the malleable nature of space and time. In 1919, observations of the deflection of starlight proved his theory and made Einstein a superstar, and so scientists turned their attention to measuring the effects of general relativity to further cement the concept. One of the weirdest of these experiments was undertaken by Joseph Hafele and Richard Keating in 1971. Their equipment was a series of very accurate cesium clocks and a set of jet plane journeys that completely encircled the Earth. To begin the experiment, all the clocks were placed in the same location and synchronized. Some of the clocks then headed off on a plane, some heading to the east and others to the west, some moving with the Earth's rotation, others against it. $7,600 was spent on flights, with 2 seats on each plane going to Mr. Clock. And because they were flying, they were in a different gravitational field to the clocks left behind. After they had circled the world twice, they were all brought together. If the universe was governed by Newton's absolute time, they should all have remained in sync. But if Einstein was correct, relative motions and space-time curvature should have de-synced them. The experiment was run, and the clocks were reunited. They differed by a few hundred nanoseconds. Einstein was declared the winner. But there is one more test of relativity that has proven to be the most spectacular. In developing relativity, Einstein found stretchy spacetime can also wobble and ring. Just as Maxwell found that electricity and magnetism can ripple, so could gravity. But Einstein couldn't decide if his mathematics were correct or if he was fooling himself, and struggled to conclude whether these gravitational waves were a part of reality. In 1974, Russell Hulse was a young astronomy student who made a spectacular discovery. With his supervisor, Joseph Taylor, whilst peering into the universe with the 300-meter Arecibo telescope, he found a pulsar, the rapidly spinning dead heart of a star. This pulsar, PSR B1913 plus 16, was spinning 17 times a second, and was not on its own, but orbited another dead star heart, a neutron star. And with the regular beats of the pulsar, they were able to accurately chart the cosmic dance. What they found, however, was quite unexpected. With Newtonian gravity, these dead stars should orbit each other for eternity. But Taylor and Hulse found that the orbits were shrinking, and the stars were slowly but steadily being drawn together. Somehow, the energy of their orbits was leaking out into the universe. And it was then Taylor and Hulse realized Einstein's gravitational waves were an ideal culprit. They delved into the mathematics of general relativity and calculated how the orbiting stars formed ripples in space-time, showing how they could carry away precisely enough energy to explain the orbital demise. In 1993, Taylor and Hulse received the Nobel Prize for their discovery, and 24 years later, the prize was awarded for the direct detection of gravitational waves. That experiment was the Laser Interferometer Gravitational Wave Observatory, or simply LIGO for short, which, with unimagined sensitivity, can feel the tiny ripples of space-time. LIGO has opened a new and exciting window on the universe. They are uncovering merging black holes and the collisions between neutron stars. And now, astronomers even plan to hunt for the oldest gravitational waves, formed in the birth of the universe. And so, in this new world ushered in by Einstein, it is clear that the entire cosmos is written in the language of gravity, of curved and warped space and time. But there was one more secret to uncover, hidden in the equations. First realized by Alexander Friedman in 1922 and later proved by Edwin Hubble, the expansion of the universe is the expansion of space, expanding from a single point 13.8 billion years ago, known today as the Big Bang. Put very simply, there was less space yesterday, and there will be more space tomorrow. Every galaxy has been found to be moving further and further away from us, bar our local group, at an average rate of 70 kilometers a second per megaparsec, which actually means that at the moment, for every 3.26 million light-years distance away from us a galaxy is, it is moving away from us at an extra 70 kilometers a second. So, a galaxy 326 million light-years from us is moving at 7,000 kilometers a second, and a galaxy 32.6 billion light-years away, it recedes from us faster than the speed of light. This may seem bizarre after everything we have learnt up until this point, but the universe's speed limit only applies to objects moving through space, and these galaxies are not moving through space away from us. Space is simply growing between us. This expanding universe makes curving and bending space-time even more complicated to understand. As equations show that space is infinite, what is actually happening is that the universe is becoming less dense. And clearly, this decrease in density is not completely uniform across the cosmos. You, for example, are not slowly drifting apart. Individual galaxies too hold themselves together due to their mutual gravity. But as this gravity is a manifestation of the curvature of space, what happens at the boundary between expanding and non-expanding space? And that is not the only problem, as expanding space makes the form of yesterday's space-time different to tomorrow's space-time, thus breaking what was thought to be one of the key properties of the universe: conservation of energy. The importance of symmetry in physics was laid out in detail by mathematician Emmy Noether, in this case a symmetry meaning that when you change your situation, the physics remains the same. Changing location doesn't change physics, meaning momentum is conserved. And the fact that physics is the same today and tomorrow gives energy conservation. But in an expanding universe, where space-time is changing, this symmetry is shattered. As space grows, it doesn't stretch. It doesn't dilute. There is just more of it. But as photons travel across an expanding universe, they are stretched and they lose energy. And galaxies are robbed of their speed as their motion grinds to a halt. In this way, energy is simply not conserved as the cosmos grows. A conundrum that causes problems for physicists to this day. And so, it may now seem that space has finally become physical, real. After all, it can bend, expand, curve, and ripple. But there is a final twist, one final rug to be pulled out from beneath us. And this can be summed up in the words of the Nobel Prize winner, Steven Weinberg. How is it possible for space, which is utterly empty, to expand? How can nothing expand? The answer is space does not expand. Cosmologists sometimes talk about expanding space, but they should know better. To the novice, this statement must seem almost bizarre. How can a leading scientist make such a claim? Well, because he is absolutely correct. In Einstein's relativity, space-time is truly nothing. The mathematics look like bending and curving, but in reality, relativity tells us space is nothing and has no properties. But what of time in this new picture? Just how were seconds, minutes, and hours affected by the dawn of relativity? To the future civilization, time meant many things. They knew that their time was unique, unshared by any others. They understood that clocks ticked differently depending on where you were and what you were doing. Their engineers had used this malleable nature of space-time in shaping their civilization. great portals of distorted time and space permitted travel across the Empire, whilst the slow ticks near the gravitational pull of a black hole had been used to stretch time and allow them to watch the end of everything. People like us that believe in physics know that the distinction between past, present, and future is only a stubbornly persistent illusion. With the coming of Einstein's general relativity, physicists were presented with a new headache. They knew that every particle in the universe had a past, present, and future, and like a line drawn on a map, they could chart the journey of a particle through the 4 dimensions of space and time, tracing out its individual world line from the past to the future through a series of nows. Each particle in your body, each electron and quark, journeys on its own world line. Before you were conceived, the world lines were dispersed, but as you grew, many world lines condensed into a bundle, which is you. And when you are gone, these world lines will again scatter. For a fleeting moment in the life of the universe, you exist as little more than a collection of world lines, a brief knot in the fabric of eternity. Whilst unsettling, this appears to make sense. So where is the headache? Firstly, we have to remember what the relativity of time really means. With no absolute time, there is no uniform cosmic clock. And this means that there is no such thing as a unique present, a true instant of now. Without an absolute definition of a cosmic now, just how do we define a unique notion of the past? Just where does the future begin? And so, headache. Within the equations of relativity, all pasts, presents, and futures are already written. The entire history of all things is already out there, somewhere. This notion, known as the block universe, has bothered many physicists and philosophers, as without a now, the cosmos simply cannot unfold from moment to moment. All we can do as we trace out our world line is follow our predefined path, and concepts dear to us, such as free will, are lost. But this cannot be correct. We clearly remember the past, and the future is a mysterious door that is yet to be opened. They are clearly different. Or are they? Consider 2 electrons hurtling towards each other. Both carry an identical negative charge and, through electromagnetism, they repel. As they get closer, the repulsion grows and their motion gradually slows, stops, and reverses. Eventually, the electrons hurtle away from each other, back the way they came. There seems nothing strange about this. But imagine we filmed the interaction between the 2 electrons, and then showed the film to an audience of physicists, playing a mirrored version, the left switched to right, and vice versa. Your audience of physicists would notice nothing amiss with the movie on the screen. Switching left and right does not alter the physics. But what if you went one step further? What if you were very clumsy, and instead of switching left and right, you switched past and future? The film now runs backwards. Time has been reversed. Your audience stares at the screen. What do they see? In this time-reversed movie, 2 electrons hurtle towards each other. They get closer and closer with their repulsion growing. Eventually, they halt in their motion and start to move away again. And with nothing out of the ordinary, the audience nods in approval at this simple display of physics. But how is this possible? If you had run the slapstick of Laurel and Hardy backwards, the viewers would have noticed, and would immediately know that something was wrong with the arrow of time. And herein lies the question: why is the electromagnetic interaction between electrons insensitive to the direction of time? And not just electromagnetism, but gravity and the strong nuclear force are also unaffected. The weak nuclear force does misbehave slightly, but it is a very tiny effect. It seems that at their core, the universe's microscopic fundamental interactions do not possess an arrow of time. Time could flow one way or the other, and they simply wouldn't care. This leaves us with a disconnect. The macroscopic, large-scale world we inhabit certainly does know about time, Cooling coffee, burning wood, exploding supernovae, these are not processes that can simply be run backwards. You cannot unscramble an egg. But with a little thought, this seems strange. Clearly, our large-scale world is nothing more than the collective properties of an uncountable number of atoms. And these atoms are interacting through a fundamental force, electromagnetism, each of the myriad of electromagnetic interactions unaffected by the direction of time. So how can such an arrow emerge from the multitude of time-ignorant interactions that take place every second? How does time emerge? In the simple view of the block universe, it stretches infinitely far into the past and infinitely far into the future. But this block universe clearly doesn't appear to resemble our own, for we know that our universe didn't stretch infinitely into the past, it had a beginning. From observations, we know that the universe was born almost 14 billion years ago. We don't know the process that brought it into being, but it was born with both space and time. Just where and how space and time came to be in the universe remains a mystery, but they have remained an integral part of the cosmos since its inception. And there are other mysteries about the birth of the universe that we don't understand. In particular, it appeared to be extremely special, being both hot and dense, and strangely smooth. And this smoothness meant that the newborn universe had a very particular property. The universe was born with very low entropy. It might seem strange that smoothness implies low entropy, as a gas spread throughout a room has higher entropy than gas all squeezed in one corner. But for matter in the universe, this smoothness meant gravity could do its work and fall together, eventually clumping into stars and galaxies. And so, as the universe expands, its entropy increases as the matter evolves. Gravitational potential energy is steadily converted into stars, planets, and people. Eventually, this energy is processed into waste heat that spreads throughout the universe. And it is this change from low to higher entropy that imprints onto the cosmos its arrow of time. Recent Nobel Prize winner Sir Roger Penrose has thought hard about our universe's initial entropy. He has concluded that the probability of this occurring by chance is 1 part in 10 to the 10 to the 123. Clearly, there must have been something special about our universe's birth. But what this was, we still don't know. And so, would this mean that the block universe has no innate arrow of time? Without the Big Bang, would it be impossible to distinguish the past from the future? Imagining how we would experience such a universe is very difficult to do. But indeed, maybe our ability to imagine anything at all is ultimately because of the special birth of the universe. On the 10th of June 1944, a British Halifax bomber was flying over France. With 400 other bombers, it was supporting the D-Day landings at Normandy, but near the city of Laval, the aircraft was struck by German flak and crashed in flames into the French countryside. The entire crew perished in the crash. 7 lives were lost, 7 lives in a war that eventually claimed millions. The pilot was a 33-year-old Dutch volunteer, Willem Jacob van Stockum, and whilst his name is not familiar today, Van Stockum was the man who discovered time travel. Of course, by the 1940s, time travel was a staple of science fiction. The Time Machine by H.G. Wells had been published half a century earlier, but this was all fantasy and whimsy and a firm impossibility in Newtonian space and time. Yet within the new world of relativity, Van Stockum had discovered a scientific basis. Mathematically, relativity is notoriously challenging. Einstein himself had wondered if his field equations would yield any analytic solutions, but merely a year after presenting them to the world, the first such solution was found. A Schwarzschild derived his black holes. And so, by the 1920s, the hunt was on for the mathematical form of the entire universe. Along with the giants of relativity, Einstein, Friedman, de Sitter and others, laying down rules, finding expanding space which itself could be curved, and even space where parallel lines could converge and diverge, some scientists explored the mathematics of hypothetical universes. And Hungarian mathematician Cornelius Lanthos had found a rather peculiar solution. His equations described a universe of dust that was rigidly rotating, and whilst it didn't appear to describe our actual universe, it was an intriguing result. Van Stockum began to wonder about the journey of particles through such a rotating universe. As these particles travelled from the past to the future, world lines stretched around the universe. But as the universe rotated, time and space were stretched and distorted. Some world lines stretched right around the universe and met themselves, forming closed loops. Along these, the future trod over the path of the past, over and over again. Physicists call these closed-loop world lines time-like paths. But in everyday language, it was nothing less than time travel. That space and time can be so warped as to allow time travel was shocking. And whilst the rotating universe might not be physically realistic, it opened up the question of whether there were other routes to the past, or shortcuts to the future. Van Stockum's goal was to head to Princeton to work directly with Einstein, but as the clouds of war were gathering, he looked back to Europe. Once his homeland was occupied, his desire was to get into the fight. And Van Stockum's own world line ended in a French field on a dark night in 1944. Whilst Van Stockum's name is now lost to history, time travel and rotating universes are not, as they were rediscovered by the eccentric mathematician Kurt Gödel in 1949. Gödel is remembered today as one of the greatest logicians of all time, and his famous incompleteness theorem still baffles today. But his contributions to physics were equally shocking. Escaping the turmoil in Europe as the storm cloud of the Second World War gathered, unlike Van Stockum, Gödel did reach Princeton University, and it was there he and Einstein became firm friends, with Einstein supporting his application for American citizenship, specifically by driving him to the hearing and distracting him from pointing out flaws in the United States Constitution to the judge seeing his case. It was at Princeton that Gödel turned his remarkable mathematical mind to relativity and the nature of space-time. And in 1949, Gödel's 70th birthday present to Einstein was a solution to the field equations of relativity. Like Van Stockum, he had found the mathematics of a rotating universe and closed time-like curves that looped around his cosmos. On receiving his present, Einstein was, in his own words, disturbed by the possibility. Gödel's wife had apparently knitted him a sweater too, but it was not part of the final gift. History does not record why. Einstein died soon after in 1955, and Gödel followed him in 1978. In his later years, Gödel asked astronomers if they had found the universe was truly rotating. The answer was always no, it isn't, and that Gödel's universe is not our own. But the possibility that Einstein's relativity potentially allowed time travel sent researchers back to their equations. Could time and space really bend back on themselves so far as to allow temporal exploration? Physicists have continued to find mathematical shortcuts through space and time, and there are now many solutions to Einstein's equations in which space and time are extremely warped. It would seem that in Einstein's relativity, time travel remains a stubborn theoretical possibility. As an example, if you add spin to a black hole, space and time twirl also, and if you dive right through the center, you might emerge somewhere and somewhen else. Another relativistic structure, a wormhole, builds a space-time bridge between two locations, and potentially between two different times, but not necessarily a shortcut. The reality of these solutions, whether they can truly exist, remains unanswered. Perhaps we will never be able to focus enough energy into a single place for space-time to bend right back on itself. We now understand how Einstein's spacetime works, but we still don't know what it is. Where can we turn next? It was not just Einstein who was charting a new path at the beginning of the 20th century. It was a dramatic period for theoretical physics, and quantum mechanics was at the forefront of the changing order. And so, perhaps, physicists thought, the answer could lie at the smallest scales in the universe. In the far future, the civilization had become desperate. The stars had long died and matter itself was starting to melt. Very few remained now, almost frozen in the darkness, the last of life grinding to a halt. But some eyes still peered into the skies to witness the last bursts of light in the universe. The great books had told them this time would come, warning them that not even black holes would last forever, whilst the immense gravity of relativity held them together. On the smallest scale, the action of the quantum world resulted in their ultimate decay. For eons they had struggled to combine the two. The world of gravity had seemed so distant from the quantum, and so too their black hole home was dissolving. They could do nothing to stop it. The last few were so very tired, they didn't even try. A university student attending lectures on general relativity in the morning and others on quantum mechanics in the afternoon might be forgiven for thinking that his professors are fools or have neglected to communicate with each other for at least a century. There is a grave at Rose Lawn Cemetery in Tallahassee, Florida. Written on it is the name of a man who died in 1984, aged 82. Unlike others in the graveyard, the man also has a plaque at Westminster Abbey in London, not far from the mortal remains of Isaac Newton. This plaque does not say much. It labels the man as a physicist and notes his birth and death. But on the plaque is also an equation, a complex mix of Latin and Greek letters. And this equation was the first unification of Einstein's relativity and quantum mechanics. The famous physicist Niels Bohr referred to Paul Adrien Maurice Dirac as the strangest man to visit his institute. Born in Bristol at the beginning of the 20th century, he did not at first seem destined for scientific greatness. In 1923, Dirac began his studies at the University of Cambridge. Famously focused on his science, he shunned many human interactions, and his conversations were mainly silent. His colleagues went as far as to name the unit of 1 word per hour as a Dirac in his honor. But whilst his speech was slow, his mind raced around the problems of physics. It was a heady time to be a physicist, with both Einstein's new world of relativity and the bizarre implications of quantum mechanics opening up. Were the fundamental secrets of the universe finally revealing themselves? When Dirac began his exploration of quantum mechanics, it was written in the past. The mathematics of Schrödinger and Heisenberg played out on the stage of Newton, with the tick of an absolute clock and Galileo's vision of space. But Dirac knew that this picture of space and time was simply outdated. Surely the equations of quantum mechanics should reflect Einstein's new visions of space and time. This bothered Dirac, and he scrambled with the mathematics trying to make it work, spending his Sundays walking alone, turning over the equations in his mind. And in December 1927, the fog began to clear. A relativistic quantum equation came into view. An equation that obeyed Einstein's demand that there is no special rest in the universe, and Dirac used this equation to explain the simplest of particles, the electron. Suddenly, various peculiar properties of the electron made mathematical sense. Within Dirac's equation, the electron spins and behaves like a small bar magnet. Both properties had been difficult to explain, but they were a natural consequence of relativity. And there was another property that was completely unexpected. If you take the square root of 1, there are 2 solutions, +1 or -1. In the same way, in explaining the electron, the Dirac equation has 2 solutions. One solution is negatively charged and clearly represents the electron. But just what does the positive solution correspond to? At first, Dirac wondered if it could be the proton, the positively charged particle within the nucleus. But being almost 2,000 times more massive, that could not be correct. He eventually concluded his equation was predicting a brand new particle, the anti-electron. This particle should have the same mass as the electron, but have the opposite, positive charge. Antimatter. The Dirac equation was the birth of quantum field theory, the most successful physical theory. It is with these mathematics that scientists can describe nearly all of the fundamental particles and forces, the basis of the modern Standard Model. And for each of these particles, there are antiparticles, electrons, positrons, quarks, and antiquarks, all a consequence of Einstein's view of relative space and relative time. But quantum field theory is built on Einstein's special theory of relativity. What of gravity and the general theory of relativity? What if we incorporate curved spacetime into the Dirac equation? Unfortunately, after such incredible early success, the last century has brought us no further in this quest. With quantum field theory, the quantum wave function that underlies existence still plays out within the arena of space and time. Because of special relativity, this spacetime is more complex than Newton's view, but space and time are still the universal stage, and this stage is broken when considering the curved spacetime of general relativity. Remember, in the general theory of relativity, space and time are dynamic and evolving. They are not simply the stage, they are players in the physics of the universe. Quantum mechanics was complicated enough, but after many years of work, its various infinities had ultimately been tamed. With curving, bending, rippling spacetime, the infinities seemed uncontrollable. With this failure to simply merge gravity and quantum mechanics, some physicists have searched elsewhere. This has involved going back to the drawing board with brand new ideas for just what space and time are in the quest for the so-called theory of everything, the so far fruitless search to tie the microscopic quantum world to the macroscopic world of general relativity and fully explain the universe. But of course, these theories of everything have not necessarily made things simpler. In one of the leading contenders, string or M theory, there might be 11 or even 26 dimensions. But what do these ideas have to say about the fundamental nature of time and space? Again, it's not so simple. In M theory, space and time are part of the fundamental structures of the universe. The strange, contorted shape of this structure in multiple dimensions explains everything, not just space and time, but all matter, all radiation, and all the forces. What exactly are these fundamental structures made of? M theory doesn't tell us. Another contender for the theory of everything is loop quantum gravity. On the face of it, this theory is even more bizarre, with space and time being quantum phenomena. At the smallest possible scale, space-time is chunky, fundamentally meshed together into a network. And to us, this subatomic mesh has the appearance of smooth space and time. But again, we can ask, what are these quantum grains made of? And again, we are left disappointed as they just are. But perhaps the solution is simpler than this. Perhaps, some have speculated, space and time do not exist at all. Remember, at the start of this story we heard about the disagreement between Newton and Leibniz. To Newton, space and time were part of reality and existed independent of the matter in the universe. Leibniz, however, said that it was the relationships between matter that defined space and time. Without them, space and time would have no meaning, and the relativistic vision of space-time seemed to match this picture. Einstein told us that matter defined the structure of spacetime, and spacetime told matter what to do. We know that in the quantum picture, spacetime appears to be lumpy, and that reality is possibly constructed of these bits of spacetime as the universe grows. But what if space and time are not really there? What if space and time are actually emergent phenomena, something we experience only as macroscopic beings? This might sound strange, but we know that we are sandwiched in the universe. This means that, for example, we don't feel the cosmological expansion that dominates the large-scale universe. And similarly, we don't feel the individual atoms as they collide with our skin. Instead, we have a collective term, temperature, to describe what is happening. Perhaps space and time are the same. In 1997, Juan Maldacena found a key relationship in the mathematics of string theory and gravity, known as the ADS-CFT correspondence. It could be accidental and of no consequence, but it could also be pointing to something deeper. The path to uniting quantum mechanics and gravity. But if this is the right path, something else emerges. Through this relationship, space and time become granular, pieces of fundamental length and fundamental time. Planck-scale pixels that set the smallest resolution of the universe. This would mean that at the smallest scales, space and time would appear as nothing more than grains of sand on a beach. And so perhaps there is no space between the grains of reality. No time between one grain and another. Perhaps to these grains, these are concepts that make no sense. There are only their relations, how they interact. For us, much larger than the scale of these grains, there is the concept of space, and somehow, through the relationships of the grains, we experience the experience of experience. But underlying this, maybe, ultimately, space and time simply don't exist. And there are just fundamental bits and pieces, and their interrelationships. This may feel uncomfortable. Just where is the you in this relational universe? Perhaps it is best to think of it like this. Most of us have come to terms with the fact that we are physically a collection of atoms. We, our consciousness, somehow emerges. We seem to be able to live with this illusion of our being. Maybe all we need to do is the same for the stage on which we play out our existence. And so, we have come a long way and are approaching the end of our journey. Space and time, our focus along our path, both seemed so natural, so normal. But we have discovered that they are far more strange, more mysterious than they first appear. Though the space and time of Newton were simple and absolute, they became far more complex with Einstein's curving spacetime, and the quantum nature of spacetime attempts to dice space and time into little pieces. But are we really any closer to understanding its true nature? A lot of hope is pinned on our next fundamental theories, that a theory of everything will eventually shine a light on the universal stage. And maybe written into that theory will be the true nature of space and time. Perhaps the block universe will be banished as the cosmos unfolds. Perhaps quantum processes are constructing a now, one instant at a time. Or perhaps some process we have yet to imagine is defining reality. Of course, nature is not bound to reveal its secrets. No matter how hard scientists work, they may never reveal the fundamental truth. We must face the fact that some mysteries might remain forever mysterious. Indeed, just what space and time actually are could forever be beyond our grasp. And so, finally, we return to the twilight of the cosmos. Within their home, the last few watched their black hole slowly evaporate. All they wanted was to eke out one more day, one more moment. But eventually, the decay of the universe could no longer be shut out. They had manipulated space, they had mastered time, but they could not defeat them. And then, there was darkness. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave a comment to tell us what you think. Thanks for watching, and we'll see you next time.